So let me redraw the circuit. So you basically have the battery here is connected to a resistor which is connected to a variable resistor connected to another resistor, then another battery. By the way guys, there is this in Money Heist episode 1 at the very end they are giving you another example which is very similar to the example of lightning and thunder. Why there is a difference between we see lightning first and thunder next. Similarly, there is very similar thing, but something, a new example is there, so go and watch the latter part. It's kind of cool. So you have 6 volts here, then this Y is 1.5 ohms, this is 6 volts, this is 4 ohms, this is X. Okay, so this is the circuit and the potential difference is 0. So how many closed loops are here? First thing, you start here, it's like you're running on a track. You start running. So this is a closed loop. You start running this way, now that's another closed loop. And you start running, now that's another closed loop. So there are 3 closed loops, and obviously you have to choose them when you're applying the Kirchhoff's second law. So first you have to calculate I, and obviously the data given, one of the most important thing that is said is that the potential difference between these 2 points is 0. So if you want to make use of that fact, then you need a loop which has this voltmeter thing. Then you have this one and this one, but in this loop you don't know about the R, so I'm choosing this loop. So you have to see how the argument filters out. Okay, you look at the mark scheme, you would see that they have applied the Kirchhoff's second law to this loop, but how would you know that you have to apply it for this loop? This is the argument. Okay, so in this closed loop, starting here, the EMF is equal to the PD. So the EMF is 6 volts. That is equal to the sum of the PDs, and the potential difference is, the only potential difference is the potential difference across these 4 ohm resistor. So you have the R, you know the current is I, so the potential drop would be I times R. So this would give you an I value of, it should give you an I value of 1.5 amps. Oh, it's 6/4. Yeah, 1.5 amps. Right? Then the B part, okay, the B part is asking you to calculate the resistance R. So when you're calculating resistance R, now there are 2 more loops remaining. You can choose this loop or the entire loop. So let's first choose the entire loop. So if you look at the entire loop, that's from here, here, if you consider that closed loop, the EMFs are 6, and since the positive is connected to the negative, and the positive is connected to the negative. We learn how to find the, like, when you connect the batteries like that, the EMFs will add up. If you have connected them like this, the EMFs will subtract. So here the total EMF would be this 6 plus this 6, and the total potential drop would be the potential drop across 1.5 ohm, R ohms, and 4 ohms. So basically the total resistance is 1.5, or let's start with R plus 4 plus 1.5 times the I value, which is 1.5 amps. So this is the Kirchhoff's second law written and directed to this circuit. That would give you an R value of 2.5 ohms. Right? So the calculation is simple, but the kind is understanding the concepts of Kirchhoff's second law and the concepts of a complete loop. Now, one beautiful thing why I said this circuit is peculiar is, now if the potential difference between these 2 points are 0, that means the entire thing is just equivalent. This entire section is just kind of equivalent to a piece of conductor, right? There's nothing special about it, because if you have a conductor here, if you replace this entire thing with just a conductor, there would be no potential difference across a conductor. There's no potential difference here and here, here and here. In a wire, as long as assuming that it's negligible resistance, the PD in a wire is 0. So if the PD here is 0, it's kind of effectively this entire system in this section is kind of paralyzed, kind of just a conductor. All these fancy batteries and circuits mean nothing. It's simply 0. Now that is Kirchhoff's second law considering the entire loop. Now you can apply it considering this loop as well. In that case, 6 would be equal to the potential drops would be the ones across 1.5 and R. So I times, and it just happened to be, this is also 1.5 ohms, and R. Okay, so in this loop the PD is 1.5 into I, R into I, and the EMF is 6. So if you look at the mark scheme, that is the second method in which they have done it. Okay.